Hello everybody. Alright, we're continuing with section 9.3, and what we're doing today is we're simply looking at some properties of definite integrals. Alright, lots of simple things, many of them are related to what you learned about indefinite integrals. Some of them are specific to definite integrals. And this is a list of 5 properties that we're going to go through today, and we're going to go through them one by one. You can pause the video right here if you want to and kind of scan through each of them, but I am on the next set of subsequent slides going to break these down one by one again, so you don't necessarily have to pause and watch right now with them. You can go on if you just want to see them one by one. Alright, the first of the properties that I just threw up on that list was this one right here. Alright, now again, notice this is for a definite integral, but what this property shows is that what happens if you take the definite integral of some function that's being multiplied by a constant. And just as you were able to with an indefinite integral, you can move that constant to the front of the integral in order to find that antiderivative. Alright, so let me just write a quick example of that. So then if I was trying to find the integral from 2 to 5 of, say, 3 times x squared minus 1 with respect to x, that would be equal to the same thing as 3 times the integral from 2 to 5 of x squared minus 1 with respect to x. Alright, very simple. Let's keep on moving. Okay, so just as with this property right here, just as with indefinite integrals, if you're finding the indefinite integral of the sum of two functions, you can separate it into the sums of two definite indefinite integrals. Or sorry, well, that was a weird statement. You can separate into the sum of two indefinite integrals. If you have the definite integral of a sum or difference of two functions, you can separate it into the sum of or difference of two definite integrals. And each of those definite integrals would have the same limit of integration. I've told you that A is called the lower limit of integration, B is called the upper limit of integration. So together they're referred to as as the limits of integration. Alright, those aren't going to change when you separate it. Alright, so very simply, here's that illustrated. Can't get much simpler, right? You just separate the sum that you're trying to find an integral of into two separate integrals like this. Keep the limits of integration the same for both of those terms. Great, let's keep on going here. Alright, this next property is not something that was relevant to indefinite integrals. What if the lower and upper limits of a definite integral are the same? Well, it turns out that anytime the lower limit of integration equals the upper limit of integration, the integral is always going to give you a 0. Alright, so the integral, say, hold up, go back. Was telling me to go back. The integral, say, from 9 to 9 of 2x to the 1/3 power with respect to x has to be equal to 0. Alright, hopefully that makes some sense. If not, I can explain in class why that's true. But I think there's a little bit of something to it that just makes that instinctive. Alright, let's keep on going here. Okay, so what if we switch the limits of integration with one another? Instead of going from A to B, what if we go from B to A instead? Well, it turns out if you just switch the order of the limits of integration, all you have to do is multiply the original integral by -1, and it will give you the integral after you switch the order. Okay, so say if we're going from least to greatest with A to B, if we switch it from B to A, just multiply by -1. Here is an example of that. Okay, you can see with the integral, all I did was switch the limits of integration from 4 to 6 to 6 to 4, kept the same function, and the result was that these two integrals are opposites of one another, essentially. So just multiply this one by -1 to compensate for the fact that you switched the order of the limits of integration. All right, and then one more property to talk about. And this one we've kind of used already in the previous video, although I didn't call it a property. Ignore that little equation over here for the moment. I'm going to put a graph on here in a second that's going to match that. If you have the integral from a to b of a function f of x dx, you can divide that interval from a to b into 2 or 3 or 4 or 5 intervals, whatever you want to, and use sums of definite integrals to add up to this one big definite integral. So say there's some number c that's between a and b. Alright, well, then instead of going directly from a to b, you could have the integral from a to c and then the integral from c to b. Alright, let me illustrate a couple things with this. And the first thing is that for this property to work, the value c has to be between a and b. Alright, I'd recommend copying that down. It's about to go off the screen. Okay, and here's where we use this. We actually used it a couple times in the previous video. You see with this picture where we had part of a function that was above the x-axis, part of it was below, and we were trying to find the area under the curve. Well, we could have, instead of finding the integral from -6 to 0, we could have found the integral from -6 to -2.5, and then the integral from -2.5 to 0, added those together, and it would have given us the same thing. In other words, watch this equation and you'll see what I mean. Okay, so instead of doing the integral all the way from -6 to 0, we could do it from -6 to -2.5, and then for the same function, find the integral from -2.5 to 0, and then add those together. It is a useful thing. Certainly, you can do the whole thing at once, but if you don't have your calculator, that's not always as easy to do as you might think. So it's often a good idea to break up an integral into 2 different parts like this, or 3 different parts sometimes. Okay, let's put these properties into practice. I have here a series of definite integrals for which I've given you the values. All right, you can read over those in the instructions, and using those definite integrals, we're going to find some other definite integrals. Starting with here the definite integral from -3 to 6 of f of x dx. Now you see that 2 of my 3 definite integrals involve function f, the other 2 involve function g. Since we're working with f here, we're going to use these right here. Alright, now this one went from -3 to 1, this one went from 1 to 6. 1 is between -3 and 6, right? If I wanted to go directly from -3 to 6, well, I could just add these 2 definite integrals together to make that happen. So here's what you would get. Okay, you can pause and look that over if you need to, but we just broke up this one integral into an integral over 2 smaller intervals, okay, that covered the same real large interval together, and added their values together. Alright, now I'm going to go through several more of these examples. If you'd like, you can pause at each one, try it on your own, and then just listen to me to see if you got it right. And I would recommend doing that with this next one. Alright, so go ahead and pause if you think you know what you're doing. Use those properties that we just talked about for integrals to find the integral from 6 to 1 of function f of x. Okay, now we rarely like to go from right to left. See, our lower limit was higher than our upper limit, and so we use that property that said you can just switch the order of the limits, go from 1 to 6 instead, if you'll just multiply the integral by -1. And we knew what the integral from 1 to 6 of f of x was, so we just had to multiply that by -1, and you got -13. Alright, continue. Pause here, see if you can find this value, please. Okay, so I used two properties here. We had a sum of two functions that we were integrating, so I broke it up into two different integrals using the same limits of integration as the original integral had. And I also pulled out the constant in front of that function f of x, put it in front of the integral. So 2 times the integral of f of x over the interval from -3 to 1 plus the integral of g of x on the same interval. There you go, 13. Coincidence is that's the same as part B. Alright, this might be a little bit trickier. See if you can figure it out real quick, and I'll come back and show you in a second. Alright, this is a little variation on the fifth of those properties here. If you want to find the integral from 1 to 6 for function g, and you know the integral from -3 to 6 and from -3 to 1, turns out you can use subtraction. Alright? Now, if I wanted to find the integral from -3 all the way to 6, I think you could agree that I would add the integrals from -3 to 1 and the integral from 1 to 6 together, right? So if I know the integral from -3 to 1 and the big interval here, I can subtract this one from the big one to find the integral from 1 to 6. And that's exactly what I did right there. And so you see how we got -16. Pretty tricky. Got one more thing to show you in this video that is kind of tricky as well. And that thing that I'm going to try to show you is what happens if you have a horizontal translation and then you have to take a definite integral. Okay? Now you see a graph that we have taken before, and I'm going to say that I translate that by a certain amount horizontally. Let me draw that real quick. And what I'm trying to show you here is that if you take a function and you shift it horizontally, that the amount of space between the curve and the x-axis doesn't change. Now, where that space is distributed changes. For instance, when I translated to the left, the area under the curve moved to the left, but the amount of area there is the same as the amount of area here, right? So you don't change the area under a curve by translating horizontally. You just change where that area begins and ends. And that's the idea when we're trying to find the definite integral of some kind of translation. You might remember from chapter 1 how if you're trying to translate a function horizontally, you either add or subtract something from its input value. Okay? If you subtract something from its input value, for instance, you're translating it to the right. Okay? And if ever you're translating something to the right, well, the way you find the integral is you just go back to the original function, but you add h units, however far to the right you went, to the lower limit and the upper limit of integration. Okay? So, for example, if I was trying to find the integral from 5 to 9 of the function f of x minus 3, well, a couple things to consider here. Since f of x minus 3 translates f of x 3 units to the right, all we've got to do is add 3 to the lower limit and to the upper limit of integration, and then we can use the original function to find that integral, because they're guaranteed to have the same area since you just shifted left and right. Okay, now similarly, the function g of x plus 1 translates g of x 1 unit to the left, and so you could find the integral for g of x plus 1 if you use the original function, but just subtract 1. Since you went to the left, subtract 1 from each of the limits of integration. Alright, let me show you that in an example, how you would use it. And I'm going to go back to the same values that we had for parts A, B, C, D a moment ago, and I'm going to add a part E and F to it. Okay? So we're going to try to find the integral from 0 to 4 of f of x plus 3 with respect to x. Alright, well here's how that's going to work. Okay, that's really just going to be equal to the integral of f of x with respect to x, but since we translated 3 units to the left, we have to subtract 3 from each of these limits of integration, so you'd be integrating from -3 to 1 instead. Now, with the information that I was given, that means that this is going to give us our value, and we're going to see that it's equal to -4 then. Need you to try this on your own. Do that for this example, and then check your answer. All right, and here you have it. Since g of x minus 7, translate g of x 7 units to the right, add 7 units to each limit of integration, and then we were able to look up here at the information where we knew what the integral from -3 to 1 of g of x was equal to, and you've got it. That's how you use some properties of definite integrals. Again, thanks for watching. Hope this has helped. I will see you next time.